This is the cover of the exam for Friday. On our Canvas page is an about exam one. I don't have a full study guide, questions, samples, things like that. You will have seen almost every single question on the exam in some fashion before. They'll be very similar to the homework questions. You'll notice there is nothing here about a formula sheet. The amount of formulas I expect you to know for this exam is very minor. Mean, median, quartiles, how to construct simple plots and frequency diagrams. That's about it in terms of what I need you to do by memory. Most of the rest of it is interpretation. Here's a result. Tell me what it means. Here's a plot. Tell me what you learned from it. Talk to me about information about what kind of data does this question gather? What sort of measurement have we got here? What would you use? Those sorts of things. Very little of this first exam is calculation driven. Moving forward, there will be a lot more calculation, and therefore you'll get a formula sheet. I don't want you to do this stuff by hand. If you have a graphing calculator, most of what we do is on here. You're welcome to use that. You're welcome to use it during exams. You can tell me what you do on it. If you've got a regular calculator, you're welcome to use that during exams. Whatever you use has to be non-connected to the internet. Questions? Okay. A lot of what we talk about when we talk about mean and standard deviation and skew and median and all of those other things is we talk about, does something differ from what we expect? Well, how do we know what to expect? Most of what we are working with are random experiments. And a random experiment is a process where we don't know what's going to happen. Instead of knowing exactly what's going to happen with our random experiment, we have a set of possible outcomes. And the collection of those outcomes is called the sample space. S can be discrete, continuous, nominal, interval, ratio. It depends on the experiment. I have here a dollar coin. The picture on the front of Millard Fillmore and the denomination of the Statue of Liberty on the back. This will be tails. This will be heads. If I asked you to tell me what could happen when I flip this coin, what would you tell me? And those are the only outcomes I know of for this coin, right? I mean, it really is potentially possible that this coin could fly through the air and somehow come to rest on its edge if we got amazingly lucky. Come on, you balanced before. Maybe, maybe not. Regardless. But we would assume for the experiment that our sample space would consist of those two outcomes. But I could ask you a different question about this same coin. I flipped this coin. How many times did it turn over in the air as I flipped it? Right? It's a very different question, isn't it? And depending on how you flip the coin, it could turn over a lot or just a little. So that would be a continuous numerical result because it might turn over a half a time, might turn over some fraction of a time. It might be discrete if we only count whole flips. That would be a very different result and a different set of outcomes. I could ask you, how long was the last phone call you made? Depending on my measurements, continuous numerical data. How many customers are in line at the financial aid office right now? If I roll a single fair die, what are the outcomes? The numbers 1 through 6. Again, I'm making some assumptions. My die has 6 sides, and they're numbered that way. Now, the word fair there, what does it mean for die to be fair? There's no predetermined weight towards one or the other, and that makes these equally likely outcomes. And again, if I flip a fair coin, I would assume that there's no bias between heads or tails. Not all events are equally likely. Roll 2 dice. Again, I'm going to assume the dice are fair. If I roll 2 dice and add the numbers, add the spots, what's my set of outcomes? 2 through 12, right? Why are those not equally likely? There's only one way to roll a 12. Both dice have to come up with a 6. But when I roll a 7, I can do that in multiple different ways. A 1 and a 6, a 2 and a 5, a 3 and a 4, and I can reverse all of those if somehow the dice are discernible one from the other. So 3, 4, and 4, 3 can be counted differently. Oh, but I just did it out loud. I didn't write it down. We are using the idea of equally likely events. What are the possible things I can get on each die to build a compound event? The chance of rolling a 7 is made up of a bunch of different individual options. I'm being a little pedantic here in calling this an event as opposed to an outcome. And that's the discernment in my head. Outcomes are usually simple, individual events, and events are whole collections of things. That's not a requirement. You can call them simple events and compound events, or simple outcomes and compound outcomes. Different textbooks use the language differently. Questions? Okay. An example. I ask you to pick a student randomly at Seton Hill. I'm going to make an assumption Pick an undergraduate student, no grad students. I guarantee you that student is part of one of 5 schools at Seton Hill: business and technology, natural and health sciences, education and social sciences, visual and performing arts. What did I leave out? VPA, NHS, ESS, BizTech, humanities. Well, somebody out. School of Humanities. And if that's an undergraduate student, they're either a freshman, a sophomore, a junior, or a senior by number of credits. So you pick a person. What are the possible outcomes if I ask you to give me their school and their class? Before I actually write them all out, how many possible results should there be? Why? Ah, so I can take the School of Business, I can take the School of Natural and Health Sciences, what did I say, Education and Social Sciences, Visual and Performing Arts and Humanities, right? And then I can have freshman, sophomore, junior, and senior. And so I can list ordered pairs for my outcomes. Business, natural sciences, education and social sciences, visual and performing arts, freshman, sophomore, junior, senior, and humanities, freshman, sophomore, junior, senior. Question: are these outcomes equally likely or not? Why not? Exactly. Number of students in each major changes, which means number of students in each school changes. Number in each year changes, right? We know exactly how many freshmen came in at the beginning of fall semester. If we go look at the registrar's office records, how many are sophomores now? How many are juniors now? Well, credit load can come in different ways, right? People can transfer in credits later, come in as freshmen, and between fall and spring, earn more credits and suddenly be sophomores by the time they come back in spring. There are fewer chemistry majors than there are music majors. So we're going to get differences by school, by year, all sorts of differences. Questions? Okay. So now I'd ask the question. I picked a student. How likely is it that this student is something? A education and social sciences junior. How likely is that? That's the definition of probability. I want to find a way to describe a probability. But the probability of event is the relative likelihood of that event in my sample space. So what started as just a general idea, by the way, this actually came up. The entire discussion of probability arose via communications about gambling and games. Two people, one of whom we only know by title, um, Knight of the Sea. I don't remember the actual name. In the correspondence and letters, asked, my friend and I are playing a game of cards, and the first person to win 3 of 5 games is the winner. But we are interrupted after the third game. He's won 2 and I've won 1. How do we divide up the pot? And that question gave rise to the entire study, eventually, of all of these probability ideas, which got more and more formalized and lead to what we're going to cover over the next couple of days. I've got an event. What is the chance that I pick a student out of this pile and they belong to the College of Engineering at Seton Hill? We have a problem. There is no College of Engineering at Seton Hill. So what's the chance that that's going to occur? What is the chance that this student is an undergraduate at Seton Hill? It's guaranteed, right? And I can say that about every event. For any event, let's call that event E, the chance that that event happens must be between 0 and 1. You said 100%, but that means 100 out of 100, 100 out of 100 is 1 per centum out of 100. Oh, which means every probability is really a fraction or a decimal in some fashion. Great. If the probability of an event is 0, it never happens. If the probability of an event is 1, it's guaranteed to happen. If my sample space can be written as a bunch of individual events, I won't even bother with this part. EI, so E1, E2, E3, I don't care if it's infinite or finite. If I can write it as a bunch of individual events, then the sum of all of these probabilities must be 1. Something's going to happen when I do my experiment. I may not know what it is, but something will happen. There's a 100% chance of something happening. If I flip this coin and ask you, is it going to land heads up or tails up? And I flip it in the air and it never comes down, the universe has gone up. We have suddenly entered the matrix and my coin is floating in midair. Doesn't work, right? Okay. So here's a question. If I give you an event A, how do I determine its probability? If I'm only counting the number of flips rather than whether it lands heads or tails, how do I figure out the chance this coin only flips over 3 times? Hmm. Well, I could flip the coin a whole bunch and count the number of flips each time, right? If I wanted to know the chance whether or not this coin would land up, heads up, or tails up, I could flip it 1,000 times and count. I could do the experiment. That's called empirical probability. So we do the experiment some number of times, little n, and count how many times we got what we wanted. We'll call that f for frequency. And then I can say that the probability of A is f over n. How many times did I get what I want out of how many times we did the experiment? But if I asked you right now, I'm flipping this coin, what's the chance it lands heads up? What would you tell me? Why? And we're making an assumption that they're equally okay, wait a minute. I can actually make that decision without ever flipping the coin, right? Assuming the theory about these things are true. Aha. So I don't actually have to do this empirically if I can construct a theoretical model. So I have to make some assumptions about the process I'm doing. We assumed it was a fair coin. We listed what we thought were all possible outcomes. We assumed they were equally likely. And then I said, 1 out of 2, 50%. This is a mathy process and will require us to count and develop tools for determining the size of our sample space, the size of our event. It'll require us to do a lot more math, to do theoretical. There is one other. Most books actually omit this and say that there are really only 2 methods for calculating a probability. But this textbook lists gut feelings. I wish I was making this up. The textbook calls it subjective probability. If you have someone with experience in a certain event, a certain thing, then you'll take their advice and their counsel on whether something is likely or unlikely to happen. Ladies and gentlemen, I give you sports betting. There are people who spend their entire day analyzing the baseball teams, who they've brought in, brought up, transferred, traded, hired, fired, etc. And then they're going to say, this is the person that's going to win the World Series. They're going to say that next week, in spite of the fact that the first spring training game isn't until next week. And the World Series is in 8 months. They'll say it now. Why? Because they have their opinions and their gut feelings and their expertise to go on. I'm of the opinion that this is wishful thinking. But there is something to be said for the pomp and circumstance around that. I only have to go back 2 weeks, right? Are we going to have 6 more weeks of winter or not? Let's check whether or not the rodent looked at his shadow. Right. Subjective. Most of the time, I'm going to disregard that. And I'm going to say we either need an empirical probability or a theoretical probability to know what the hell is going on. But notice both of these really do measure the same way. We count how often A appears in our set. And then in our previous one, we counted how many times A actually happened when we ran the experiment. As N gets bigger, these 2 numbers get closer and closer together. If we have calculated the theoretical probability correctly, we will see that the empirical result gets closer and closer to the theoretical probability. This, by the way, is called the law of large numbers. And this is why insurance companies exist, why casinos always make money whether you win or lose, and why we as data scientists and business people want to understand a theoretical model. Questions? Problem with doing this is the experiment might be costly. It might be expensive. It might be difficult. Every repetition of the experiment must be exactly identical. I have to do exactly the same way every time. It is possible that outside factors may prevent me from doing this. Look at the FDA trials for the COVID vaccine. If I really wanted to make sure that the COVID vaccine was guaranteed to be effective, I would have run longer and longer and longer trials, but I couldn't afford to. The federal government, couldn't afford to. People were dying. Now, did they run enough trials for us to be sure that the vaccine is safe enough? We'll have to figure out what safe enough means and how we could mathematically define that and see whether or not it works. Are repeated trials even possible? Sometimes. We're talking about bumpers last time. If you do the trial, the bumper breaks. I can't repeat the trial. I get a new bumper and try it again, but then it might be different. So I have to worry about variability. Questions? I'll go back to my coin. I'm going to flip that coin 10 times. What should happen is different than what will happen. If I flip that coin 10 times, I may not get 5 heads and 5 tails. Page 158 shows me the first 10 flips. Oh, it was heads. It was heads twice. It was heads 3 times. Oh, then I got a tail. Then I got another tail. Then I got a head. Then I got another tail. I ended up at 50%. But notice that if I do another 10, well, then I started getting more heads, and then I got more tails, and then I got more tails. And notice how we're wobbling back and forth. We're getting closer to 50%, but we're not guaranteed to be there. And once you get above 50%, we had a hell of a streak here, didn't we? Bunch of heads in a row. And then we started to wobble a bit, and we get closer and closer to 50%. That's our law of large numbers in action. It is highly unlikely that you will have a 50% guaranteed result at any point in this game. But in the long run, if enough people flip coins long enough, we will see something that approaches our theoretical behavior. So let's look at that theoretical behavior, because that means I don't actually have to do the experiment. If I can figure out what's going on theoretically, I might save myself a bunch of money. Let's suppose I look at my sample space. And I can write my sample space in a set of equally likely elementary events. Now, an elementary event was basically just one thing. It wasn't a combination of things. It was just one thing. And I have to be able to write this out in advance. Written out as a set in advance of any experiment. Then this is just a counting game. All I have to do is count the number of outcomes that actually contain A and divide by the number of outcomes in my sample space. Now, I wrote outcomes instead of events because I think of both simple and compound events, and I want to differentiate between the two. These are simple, elementary, single events. But these are in advance calculations. These have to be done ahead of time, and they have to be based off of mathematical rules and ideas about the event itself, the outcomes, and the experiment. And these are not always possible in business situations. Things like dice and coins and lotteries, I can do those directly because they're independent of people. As soon as human emotion or opinion or that gut feeling, subjective behavior comes into play, I have a problem. And I won't always be able to do that. When I ask you, will the stock price of, pick a company, rise or fall in the next month, that's a subjective probability. I need to know a lot about that particular stock. I need to know about the politics surrounding the policies that will change how that stock works with. And there's a necessary minimum requirement of knowledge to subjective probability. But doing the theoretical probability, that calculation looks very similar to our empirical probability. In our empirical one, it was how many times did what we want happen, of how many times we did the thing. Out of this one, it's how many times could what we want happen in all of the possible outcomes out of how many outcomes there are. And that's where my 50-50 with flipping my coin came from. There were two outcomes, and one of them was the one I wanted. That's exactly this fraction. There is a 75% chance that Streeling University's fall enrollment will exceed last fall. Empirical, theoretical, or subjective? What kind of probability is that sentence? And why?
It's theoretical because we don't have the data for the next semester.
So how am I going to calculate in advance chance of increase versus chance of decrease? Then I'm not actually doing this theoretically. I'm doing it empirically. I'm looking at the last few years. Now, if I'm in admissions, maybe I have a feeling about this because I see all that data. So it could be subjective. And if I then say, no, here are the last 20 years worth of Streeling University enrollment data, then you might be able to make an empirical result. I don't think I can do it theoretically because of exactly what you said. I don't have any information about the upcoming class. I can't make a priori calculations on that. On the other hand, look at number 13 here. The probability that a randomly selected student in your class is celebrating a birthday today is 1 in 365. Empirical, theoretical, subjective. There are 365 days in 2025. There's a chance somebody has a birthday today. I don't know if it's any of you. I don't know. But that clearly based on the idea that everybody's birthdays would be equally spread throughout the year, that's a theoretical idea. Number 15. Based on the reported experience of climbers from a given year, a climber who attempts Everest has a 31% chance of success. Empirical, theoretical, subjective. Exactly, because it says right there at the beginning, based on the experience of climbers from a given year. We have experiments. People tried to climb Everest. 31% of them succeeded. We think you have a 31% chance of success. So notice, I didn't ask you, are these right? Are these wrong? Are these true? Are these false? I just asked what kind of probability we're getting here so that we could figure out which way they got it, and then whether or not we agree with that definition, make further predictions and results. Questions? Almost all of the rules of probability are based on ideas from sets. Which means a lot of the language that we use to describe a probability is set theoretic language. Which means I'm going to sound like a real geeky SOB for a little bit, but it gets translated into English fairly directly, I believe. And a lot of it has pictures you've seen before. An event A is the subset, a subset of the sample space S. Okay. In that case, I'm going to think of my sample space as the universe in which my outcomes live. This box. And then I pick some of them and put them in a blob here. That's A. And again, there are individual outcomes all over the place. An easy, in my opinion, an easy example. Pick a letter from the English alphabet. What is the chance it's a vowel? Vowel is my event. And the set of English alphabet letters is 26 letters long. How many vowels are there? A, E, I, O, U. There you go. So I know exactly the 5 things that are in the set vowels, and everything else is in the set letters that are not vowels. That's the outside of my circle, right? The set S take away A is the complement of S, of A. That gets written a number of different ways. Sometimes it's written A prime. Sometimes it's written A with a superscript C for complement. Sometimes it's written A bar. I believe this textbook uses A prime, but 2 of my other books use each of those other notations. That's why I thought I'd mention it. I see them in a lot of places. But wait a second. If I'm dealing with vowels in the English language, a letter is either a vowel or not. Okay. But that's everything that could happen, right? So the chance of not getting a vowel is the chance of getting a vowel taken away from the chance of something happening. Well, something happening was a 1. Something has to happen. That's a 1. Or another way to think of it is this statement. You're either not a vowel, you're a vowel, That's every possible result. That better add up to 100%. That better add up to 1. But I didn't actually say that sentence in correct English. A letter is a vowel. A letter is not a vowel. Grammar time. There's a conjunction that goes in the middle there. What word should you put between this is a vowel, this is not a vowel? Or. Aha! The word or should be related to adding. But there's a set picture here. If I have two options, right? If I have two options, maybe I could do one, maybe I could do the other, maybe I could do both. So let me change from letters to cards. Standard deck of playing cards. Now, I say this with a straight face, with all seriousness. Does everybody know what is contained in a standard deck of playing cards? Has anyone not been familiar with a deck of cards? Okay. There are 13 individual values, 1 through 10. The 1 is an A, ace, and 3 face cards, a jack, a queen, and a king. They come in 4 varieties, 2 of which are black, clubs and spades, 2 of which are red, hearts and diamonds. So 4 suits, 13 values. There are many games played with different decks of cards. There's a very interesting game played with a 5-suited deck. The 5th deck can be anything. I've seen it in Eagles. I've seen it in Crowns. I've seen it in all sorts of places. There's a lovely game played with 2 decks of cards, 104 instead of 52. There are many decks played with lots of many games played with lots of decks of cards. But let's consider this word or. What is the chance that you get a queen? Pick a card, any card. What's the chance you get a queen? The chance itself has to be between 0 and 1. So 4 is a count. There are 4 queens in the deck, right? But there are 4 queens out of 52 cards. So if I think of this as a theoretical probability, I'd write it like that. You could simplify this fraction if you wanted. You could write it as a decimal if you wanted. That's not going to bother me how you write it. I prefer fractions to decimals most times because I think in fractions. But that's me. You want to use decimals? Then we have to worry about where you round. We'll talk about that more in a bit. What is the chance you get a red card? Because there are, wait a minute, red card.
Oh, right, 1 and 2.
Yeah, there are 26 red cards, 13 hearts, 13 diamonds. So 1 and 2. What's the picture look like? Well, now I have 2 different sets. I have the set of red cards and I have the set of queens. Cards, red, queens. What's that? we'll talk about that. And the other ways we can write things in here, more set descriptions on Wednesday. I will see you all then. Please remember, your chapter 4 homework is due on that day. If you have questions or questions regarding the exam, please come to my office hours and bug me. I will see you all then.